Not until the mortgage done.
I think someone should yesterday I'm caught up until Friday, which I know is only 3 days.
Morning, everybody. I don't think there's any announcements or business I have to make, which means I'm worried. When's homework due?
Monday.
Due Monday, right? And it's got lots of hairy vector stuff in it, right? So come to grasp to get help, right? But we are moving on, plunging forward, and we gotta get started on chapter 22. And there's no better way to start a chapter than to give a quiz. Let's do a quiz. Talk. Normally I would do concept first and then math. We're going to flip that just slightly and do math first. Not slightly. We're going to do a complete 180 and do the math first, which is not what Michael Faraday did, by the way. This is his idea, but mathematically he wasn't that good. Through no fault of his own. More on that later. So, the electric field, by definition, okay, is the electric force, a la Coulomb's law, divided by charge. And it's kind of a special charge. It's called the test charge. The whole reason we are about to talk about the electric field in great detail is because Coulomb's law is hard. Coulomb's law is mathematically involved. Coulomb's law, with all of its vectors and things, can be trouble, as you're finding out on the homework, right? Okay? Can be really, a lot of detail in there. And so it would be nice if we could step away a little bit from that and maybe come up with something that allows us to visualize better what's going on, that maybe takes a little bit less mathematical rigor. So the electric field is a step in that direction. It is not the destination, because the electric field is still a vector. You see the vector symbol on top, right? So vectors are still here, okay? However, the electric field does allow us to essentially ignore one of the charges in our collection of charges. What do I mean by that? Let's take, so this is like the mathematical definition, okay? So if we've got a point charge, let's back up. Coulomb's law. Okay, Q1, Q2, all over R squared, right? And I'll use the R hat version right now. Okay, so if I've got a positive charge and another positive charge, right? We know that the force between these two charges is going to be away from each other, right? Okay. So what if I just sort of said, okay, I'm going to call that one Q naught. It's like a test charge. It's like a charge that I can kind of move around and sample in space, right? And I'll use big Q as the thing that's like causing the force on the test charge. We know the test charge exerts a force on big Q, but we really want to look at the force that's going on the little test charge I'm going to move around. So just to get the idea here in sort of an animation, right? I can pick this up and just move it wherever, right? Okay, and figure out what the forces are going to be on it. The electric field allows us basically to not worry about the magnitude of this test charge and determine what's going on around big Q because of what big Q is. It's taking one of the charges out of our consideration. And how does it do it? Well, if I write down Coulomb's law for this situation, that would be K, big Q, and then my test charge, and then R squared. Let's just do the magnitude for now, okay? And then if I write down the electric field magnitude, it's that force, K, Q naught over R squared, divided by Q naught. And I know it seems like a stupid math little trick. Well, Mr. Bailey, you're just dividing by a charge. So what? But look, the electric field equation, what's the only thing that makes electric field? Big Q. Now, this is a huge conceptual leap, right? No law. So in Coulomb's law, we're having to worry about what the test charge is doing, right? But in the electric field is created by big Q. It's created by the thing that has charge on it. And all around that distribution of charge, there will be a pattern of vectors, a field, a lay of the land, right? That tells me what a charge is going to do in that field. And this really was kind of the genius of Michael Faraday. He was so good at visualization and coming up with these ideas. And then his ideas had this incredible analytical results, right? That others would pick up from his concept, from his ideas, and formalize it in the mathematics. The reason Michael Faraday wasn't good at math was because of his upbringing. He was not well educated because of his poor circumstances growing up. In the class-conscious Victorian society of the age, if you weren't born into the right class level, you just didn't get an education. Some of you are like, well, that's happening now, Mr. Bailey. And you're not wrong, right? But it's a little bit more equal than it was during the Victorian age. At any rate, okay, that doesn't belie the fact that the electric field is one step down the road of having less to think about, less to keep track of, which is kind of nice. All right, I brought my Van de Graaff generator here today. It does not generate Van de Graafs. What it does is it's like a really fast version of rubbing your shoes on the carpet over and over again. If you ever like rub your shoes on the carpet and then tried to grab like a doorknob or the refrigerator or something like that, what happens? A little shock, right? Driving around hot, dry days in Fresno, get out of the car, right? The rubber on the wheels has been running over the asphalt, it picks up charge, right? And then you ground yourself or discharge it, right? You get a nasty zap. Pet your cat too much and then touch its nose and your cat hates you. Well, the cat hates you anyway. But yeah, so you get these static charge. So basically the Van de Graaff generator builds up a lot of static electricity on its dome, okay? I have taken this rabbit fur here, okay, and I've placed it on the top of the dome, and I haven't tested this today, so we're going to see what happens, right? But let's see if I can get an electric field that you can see. Ah, there we go. You can hear it, can't you? Right, okay? But there's an electric field there. The rabbit fur picked up because it got charged. All those charges want to be away from each other. But I want to show you that I can interfere with this field. You see that? Right? And come in. Woo! Woo! I have the force. Right? Okay? But you see, right? There is something around this dome that I can interfere with and cause the rabbit fur to do all kinds of stuff, right? Okay? The electric field from this dome exists because there's charge on the dome. I don't have to worry about some other charge like what it's experiencing. This thing has an electric field. Another parallel to this is the gravitational field of Earth, right? Why does the Earth have a gravitational field? Because it has mass, right? Does it matter if the moon or the International Space Station or rockets are in orbit around the Earth? Do those things change the gravitational field of the Earth? No, okay? The Earth's gravitational field exists because the Earth has mass. And if the Earth's mass isn't changing, and its density isn't changing, then the gravitational field is going to stay the same. Electric fields The electric field of a point charge, a single charge in space, depends on what? The charge that's making it and how far away you are from that charge, right? The further away from the thing that's charged, the weaker your electric field is going to be. This is powerful, right? Now, of course, the electric field, come back. Electric field is a vector, right? KQ over R squared with an R hat. And we can do the R cubed thing where instead of writing down R hat, we write down R vector. Okay? And now you might start seeing a little bit in this chapter why I primed you in the last one to start thinking about R vector. For example, if I've got a positive charge right here, okay, and I've got another charge and a point in space, this doesn't even have to be a charge, and I want to find the electric field here, where's your R vector going to start? On the thing that causes it. What are we looking for? We're looking for electric field right here, right? Well, what's causing the electric field right here? This thing. And then I just draw my R vector to the point where I want to see it. What if I want to find the electric field down at this point? Now, and it's my distance automatically, right? I don't have to worry about what R hat is or whatever, right? Okay, so it's going to start paying dividends now. Let's do an example. This example mathematically, so this is a little bit like a repeat, okay, of the example that we had last chapter. Remember the 3 charges I had together? Find the force on one of them. This is similar. I've only put 2 charges. If I put a third charge at point P, let's just do a what if. Don't write this down. Let's say I put a charge right there. Well, what's the electric field at that point going to be? What's the distance to that charge if I'm right on top of it? 0. And what's KQ divided by 0 squared? Undefined. It's not your fault. It's not. Math teachers. Why did the world afflict us with math teachers? Okay, so why do mathematicians say that a divide by 0 is undefined? Because what? No. No. It's because there is no algebraic operation that can be defined that would give you 0. Did anybody understand that? Not really. That's stupid, right? Because everybody knows that you never divide by 0. You approach it, right? You get closer and closer to it. And eventually it gets so small that when you divide by really, really tiny things, what happens? They get bigger and bigger and bigger, right? So is it any kind of stretch of the imagination that if you divide by smaller and smaller things, you just get bigger and bigger and bigger? And what's the end of bigger and bigger and bigger? Not undefined. It's infinite. So the electric field will be infinitely large at that point. Okay? So that's why you don't ever find the electric field of a charge at a point. Like the charge is never at the point. The point just has to be in space. Okay? We want to find the electric field at point P because charge 1 and charge 2 exist. Well, we know kind of how to do this. We can borrow some of the problem-solving method that we did in the last chapter and move it forward. If I've got 2 charges and they're both causing field at a point, what's the game plan? How do we attack this?
Find the electric field of each.
Electric field of each one separately, and then add those vectors together at that point, right? It's that method of, okay, I got lots of stuff, isolate one at a time, figure out what they are one at a time, and go. Okay, so what does that look like? Well, that means that if I want to find the electric field at point P, I've got to find the electric field of charge number 1 and the electric field of charge number 2. Why are there not 2 subscripts?
Because we're only dealing with one charge.
Not just one charge. The electric field doesn't care about that other charge, right? We're not talking about the interaction between 2 charges. We're talking about the electric field in a point in space because of a charge, the charge that's causing it. So already there's a simplification just of the subscripts, right? Not having to keep. Many of you have been coming, Mr. Bailey, is it F13 or F31? Well, guess what? It's just 1 now, right? Okay, whatever your charge, and you're done. Like it's so nice. It's so. Thank you, Michael Faraday. Okay, so how do I find the electric field from point 1? Do we know the electric field of a point charge? Right there, right? It's sitting right there, okay? So it's K, and then what charge do I put in? Q1. Oh my gosh. And then what's the distance vector going to be? R1. I just will put R1 in for now, okay? And we can do cubed, and then R1 vector. I'm using the same method that I used last time for the forces, right? So the question now becomes, what's R1 vector? Well, R1 is going to start on charge 1 and end at point P. It's right there. So R1 vector is AJ hat. I drew it, I can see what its length is, and I know what direction it's going, right? So that means that my electric field is going to be KQ1 over A cubed, because that's the magnitude of that R vector, times my R vector AJ, and it's KQ1 over A squared J hat. Okay, so I found my E1. And I can put in numbers now, right? Just for completeness sake, it would be 8.99 times 10 to the 9. Q1, and then plus 7. Do signs matter? Using the R vector method, you want to make sure you put the signs of the charge in. Plus 7 micro times 10 to the minus 6 coulombs, all over 0.4 squared J hat. I got 3.9 times 10 to the 5. Oh, what are the units? We can talk about units. What are the units of the electric field? Look at the top box. Newton per coulomb. In the J hat direction. Okay, so there we go. Got E1. All right, let's find electric field because of point 2. So spell it out for me. K times what charge? Q2. You realize there's like no guessing here, right? Okay. If it's the electric field of charge 2, then it's charge 2 that goes into it. I need R2, D2, 2 vector. So what is the R2 vector going to look like? So where does R2 vector start? On charge 2. Where does it end? On P, the place that we're trying to find it. R2 vector is this one. And can I just kind of look at it and know what its components are? What's the x component of R2? It's a B in the negative I hat direction, isn't it? Because it's pointing to the left, right? We got to go left and then up. Okay. And then the y component, what's the length of the y component? A, and then what direction? J hat. Okay. So I can kind of clean that up a little bit, right? That's the same as saying negative B I hat plus A J hat. Okay, there we go. So that's my vector. How do I find its length? It's going to be the square root of B squared plus A squared. And now, Mr. Bailey, you're messing with me because everybody knows that A is squared plus B squared. Square rooted is C squared. I'm not sorry. You really need to get away from A being X and B being Y. It's just simple. Okay, that's 0.3 squared plus 0.4 squared, square rooted. I don't, is that that's 0.5, isn't it? The 3, 4, 5 right triangle. All right, so I have that. Okay, and now I can go ahead and write down what E2 is. It's going to be KQ2 all over, I'll just put 0.5 cubed, and then it's going to be negative B I hat plus A J hat. So E2, the vector E2, the electric field vector E2 has two parts to it, right? So I've got to make sure that I write out all those parts. And I won't put the numbers in there. I did get, when I put the numbers in, my E2 became 1.1 times 10 to the 5th I hat minus 1.4 times 10 to the 5th J hat. And that's all newtons per coulomb. And now that I've got a component there in the J direction, and I've got two components here, what do I do with those two vectors? Put them together, right? I's with I's, J's with J's. And then I get that my electric field at point P turns out to be 1.1 times 10 to the 5th I hat plus 2.5 times 10 to the 5th J hat. From just that description, what quadrant is this electric field at point P pointing? Quadrant 1, isn't it? Positive X, positive Y, right? So it's kind of doing some sort of something like this, okay? Ooh, that's interesting. We haven't done the concept yet. We haven't done really the pictures, okay? But if you had to take a stab, if you had to take a guess as to what direction positive charges cause electric fields to point, what would you say? Away. They point out. What would negative charges, what direction do those fields now point? In. So in fact, charge number 1 is trying to push outwards with the electric field. Charge number 2 is trying to pull inwards with the electric field. So if it's pushing out, but also towards, it kind of gets that vector cocked off to that direction. But I wanted you to see first the math. I wanted you to see what looks better, this or what we did with Coulomb's law? This. You're like, Mr. Bennett, why are we complicating these with an electric field and another idea? And now you know the spoiler. Faraday's lines of electric field, which I'm about to show you, don't exist. They're not real. He thought they were real. They're not real. And yet, we are still going to teach it to you because it is such a powerful way to visualize what's going on. We're going to do a whole lab where we do nothing but draw these things, okay? But not next week, a couple weeks from now, okay? So, but I wanted you to see that just by eliminating one of the charges as an active player, we can simplify, right, what's going on. So, let's do the idea here, okay? I showed you the videos yesterday, and they gave you some sort of visualizations as to what's going on with this field. What I want to do right now is play you a couple of these videos. They're excerpts from the video you already saw. So this is like the second time through, which I, again, think is just a good way, right, to reinforce what's going on here. Is this going to work? Of course not. This. Stop taking over the screen. Here we go. All right, let me contrast a little bit better. Whoa, I'm going to sleep.
Anywhere in the vicinity of an electric charge, a small test charge experiences a force. If it's due to only one charge, the pattern of forces detected by the test charge is simple.
Why is that vector getting bigger and smaller? Closer or further away, right? The closer you get to a charge, the bigger its electric field is going to be, right? And therefore, the bigger the force the test charge. They're showing you a force vector here now, right? Okay.
The pattern's more complex for two opposite charges.
It like pointed in towards that one, right? And away from the red towards the blue?
Or for two charges of the same sign.
Always pointing away from them?
And more complex still, for more complicated arrangements.
You like the trippy music?
But in any case, here's the point. Even if the test charge isn't there to feel it, the pattern of forces can be imagined to exist everywhere in space.
What did you just say? Even if the test charge isn't there. In other words, does the test charge matter?
No.
No. When we're thinking about the field, doesn't matter what we're using to sample it with, that field exists because the charge that's causing it exists.
This is the essence of the idea of the field.
It's a pattern of forces that exists around something.
And although Faraday only imagined it, the field can also be expressed mathematically.
I hope you see it's in 3 dimensions, right? And then scary math.
The force that acts on a test charge at each point in space is equal to the test charge times a quantity due only to the other charges. That quantity is the electric field.
The field only depends on that charge that causes it, right? Can we find the force? If we put another charge in the field, can we find the force on that charge?
Yeah.
Yeah, what do we do?
Multiplied by that charge.
Whatever the value of the field is, multiplied by the test charge, we're done. We got the force, right? So from here on out, you want to find Coulomb's law force on a charge? Find the electric field first, right? Hey, Mr. Baylor, where were you yesterday when I was doing my homework? I was preparing this lecture. Right? It's just cleaner, right? Better. So, what Michael Faraday was imagining was something that nobody had imagined before. This pattern that existed around all things that had charge. And since charge is an intrinsic part of what makes up our universe, he was talking about fields that exist everywhere. And so he grappled with how to draw these fields, how to understand what they did, how to use this conceptual brilliance and visualization power to make predictions and figure out what was going to happen. And so what he did is he connected these charges with lines of force. He actually started off calling them tubes, tubules of force, okay? Faraday grew up in a scientific era when the idea of action at a distance was still very much not in vogue. Like, Newton was the first one to come out and say, oh, well, the Earth is held in orbit because of gravity. And everybody's like, well, where's the string? And Newton's like, no string required. That was like kind of one of the huge leaps that people had to take to believe Newton's laws of gravity. It was because there's not what's connecting it, right? Okay. And so in that idea, Faraday comes along about 150 years later, and still science isn't comfortable with this idea of action. I mean, think about it. We are used to action at a distance, aren't we? Like Wi-Fi. How do we get information? Is it through the tubes? Well, wait, the internet's a series of tubes, right? Right? No, like, right? We know it's radio waves, we know it's, right? Okay, all that kind of stuff, right? We're sort of comfortable with this idea, so it's kind of like make fun of, oh, Faraday, we're using tubes. It's what they had, right? They had to have some physical connection between things in order to know that they were there, right? But it is such a powerful picture that we still use it today.
As Faraday imagined it, this something would be lines or tubes, each one capable of applying a force to any charge in its path. These lines of force would begin only on positive charges and end only on negative ones. And they would flow smoothly through space, never crossing or tangling. No matter the configuration, the charges would have a characteristic pattern of lines. The force they applied would be strong near the charges where the lines are crowded together, and weak far from the charges where the lines are farther apart. The ability to apply a force resides at each point in space, and the force arises from the intensity of lines, regardless of the location of the charges that create them.
Okay, that picture right there, do we see any charges besides the test charge? No, we don't even see the charges creating that field, right? But we don't have to. We know there's a charge down on the left-hand side, so we know it has to be positive because those field lines are flowing away, right? Where is the field weakest, right or left side? The right side. How do you know? There's less lines on that side, right? The lines are closer together on that. So there's a lot of really good information to be taken out of an electric field diagram that's using these electric field lines. Did you catch some of the rules that Michael Faraday came up with?
They start at positive.
They start, an electric field line always starts on a positive charge. That could be at infinity, but it starts on a positive charge. And where does it end? On a negative charge. Are lines allowed to cross?
No.
No, they can't intersect. They can't be in the same place at the same time. Okay? They'll curve away or push away from each other. Okay? So they start on positive, end on negative. They're not allowed to crisscross. Okay? And the number of lines that you draw on something should represent how strong the charge is. So for example, if you've got one charge that's got 2 coulombs on it and another charge that's got 1 coulomb on it, if you draw 8 lines on the 2 coulomb charge, you probably draw 4 lines on the 1 coulomb charge. You're just trying to indicate relative strength with the number of lines you would draw. Okay, so how do I do this, Mr. Baylor? Well, okay, you're going to have a whole lab on it later in the next unit. But let's just do a couple so you get the idea. So you know when you're looking at pictures in the book, looking at pictures online, looking at pictures in your homework, you have an idea, right, of what you are looking at. So I've got a positive charge here. It's the only thing in the universe right now, okay? This positive charge. So we're going to draw the electric field around this positive charge. Well, where do I draw a line? Where does it start? On the positive charge, right? And which way does it go? It goes outwards. So we draw these lines, and they weren't doing it in the video because it gets a little bit confusing, but when we do it on paper, we do indicate with arrows the direction that field is going. And how do you know when you've drawn enough? When you have an idea of what the field is doing, okay? From this one, I can see that this field is going outwards in every direction, right? I could draw more lines, like I could draw the lines that go here. And then how do I know they do these? Because I've done this a lot. No. Because I know that the electric field of a positive charge needs to spread out smoothly and uniformly in space. If that's all there is, right? These field lines don't want to tangle or cross, and so those field lines will try to get out away from each other as fast as possible, okay? Spending as much time getting as far away from each other as possible, right? So that, in other words, I'm not going to draw a picture, right? My picture's not going to be positive and then just this, right? Okay? Because if all I'm going to do is draw 4 of these lines, I really should draw the ones that are furthest apart from each other around that charge, right? Okay. So that's what a positive charge would look like. Okay, so different universe, negative charge, all by itself. Okay? What would this drawing look like? The lines, where do they start? Somewhere else. It's right? And where do they end? On the negative charge, right? So I would draw lines. You can cheat and draw them going out, starting on the thing and then going outward, because sometimes it's hard to go from infinity down to the thing you're trying to hit, right? You can see I screwed up that top one a little bit, right? But importantly, I would put the arrows directed inwards on that charge. Now, if I was comparing these two pictures, which of those two pictures has more charge in it? The positive one. Why? I drew more lines. Right? So this is kind of the idea of the rules that Faraday came up with to explain his pictures. And the reason Faraday was applying these rules is because he wanted predictive power. He was a scientist, right? It wasn't enough to just philosophize that something was going on. He wanted the ability to predict what was going to happen. For example, let's take this and kind of move it up and away, and let's get this and shove it up in the corner. I love iPads. All right. So let's do a positive charge and a negative charge right next to each other. Okay? Now, we know that the field lines have to start where? On the positive. And they're going to want to end where? On the negative. They're going to want to take the shortest path they can take. Okay? So in other words, it's not going to do this. Okay? It's not going to do that. Right? A field line leaving the positive charge will just draw a straight line and terminate as soon as it can on that negative charge. So the field line for my positive charge, if it was all alone in the universe, the one that's going to the right, okay, will just come in and terminate, right, on that line. Okay. But what about a field line that starts going up here at like this 45-degree angle? It wants to move away from the positive charge, right? But it wants to take the shortest, easiest path to terminate on the closest negative charge it can. Well, is the closest negative charge at infinity? No. Where's the closest negative charge? Right there, right? But it's not going to come out, go straight, and then down. It's not going to do that. It's not going to go like that. You got to draw smooth. That wasn't very smooth. You kind of have to draw a smooth curve. No kinks in these lines, right? It's a smooth curve. So I'd have that, and I would draw an arrow on it indicating direction it's going. Maybe one down here, okay, doing something like that. One up here could come around and do that. That wasn't very smooth, but you get the idea, right? Something like that. Okay, now we get to the ones that are on the other. So like this one over here, coming out over on that side, okay? We kind of have a choice. Like, could it, do that? Sure. And there's probably one that does that. But there might be a faster way to get to infinity, or a faster way to get to a negative charge, which is in that direction. But this field line, where does it have to terminate? At a negative charge somewhere, right? Well, we've got one right over there. It turns out the fastest way to get there is to go to infinity, wrap around, and come back the other side. I don't have an infinitely large screen to draw that for you, right? But the idea here is I have to have an equal, so right now my drawing is wrong. How many field lines do I have coming off this positive charge? 1, 2, 3, 4, 5, 6, 7, 8. I have 8 field lines coming off that positive charge. How many are on the negative charge? 6. So either these charges are different in their magnitudes, but I didn't say that. I said I just have one positive charge, one negative charge. They're equal in magnitude. So how many field lines do I have to have on the negative one? Same number. I have 8. So this one, where does it go?
From the top right to infinity.
Goes to infinity, wraps around, and ends up on the negative charge, right? And so on and so forth. Okay? To get the full path. Now, does this drawing mean that there's no electric field up here? No, there's electric field up there. Why is there electric field up there? How many electric field lines would I have to draw to represent the entire field? All of them, even an infinite number, right? I'm not going to do that. I'm going to draw enough to get an idea for what's going to go on. For example, if I dropped a positive charge right there, can you predict where it's going to go? Like the path it's going to follow?
Yeah.
What does that path look like? Yeah, it's not going to go, woo. It's going to follow the field lines. Because the field lines are a representation of all of those force vectors and how those force vectors are changing their directions in space depending on where it is. And so you look at the field, so if I had to draw the actual field, not the lines, because the lines are a lie. We know this now, the lines don't exist, right? But if I had to draw, here's a negative charge, I'm like, okay, so force vector, that would be that, and that would be that, and then that would be that, and then the one, and then over here, and then it gets messy having to draw all those little tiny vectors. And even the force vectors can cross over each other and do some weird, because if I want to draw the force, right? It's not pretty. Physicists have actually come up with different ways to visualize these vector fields using kind of almost like heat maps or contour maps to get away from having to draw the arrows, because the arrows can get confusing really fast. However, this is elegant and simple, and in the age before computers was easily free-handed, right? If you got good at the drawing, you could really, really predict any arrangement of charge. You could kind of get an idea for what the field was going to do. So, what is the field going to do around this dome? What do you think? Look at its shape. It's going to be outward, isn't it? So, why is it when I put the thing on and turned it on that the hair went outward? It's following the electric field. Right? And so this is what Faraday was really trying to do in describing why charges did what they did and how they interacted with each other. It's an absolutely brilliant way to go about doing it. And Faraday would go on to invent the world's first electric motor. He would lay the groundwork for the world's first wireless radio transmission across the English Channel. Everything that you know and love about the internet, or hate, has come about because Michael Faraday sat down one day and said, I'm going to figure out how charges work. It's incredible. Am I saying Michael Faraday was the only one that would have done it? If we hadn't had Michael Faraday, we'd be living in steampunk? No. Okay? Eventually somebody would have figured it out. But Michael Faraday kicked that ball down the hill and got it rolling. How many electric motors are there in your life? You're carrying one around in your pocket right now. Do you know there's a motor in here? It's a little tiny vibrating thing. We could argue about whether or not it's a motor. But every time this thing does a haptic buzz for you, okay, it's based on Michael Faraday's original idea. I'm not saying there's a little piece of mercury and a piece of cork in here spinning around. I'm just saying that these ideas, this is where we are going, right? We are going to invent our modern society and all of our technology. It begins right here. It's phenomenal. It's phenomenal that we were able to kind of put all of this together. Okay, so I showed you those videos. So now it's time for another quiz. Tying everything together we know. Let's find the electric field. Yeah, because I'll do that one later, okay? So it's all fine and good to be able to find the electric field of like 1 or 2 points, right? What we need to find, we want to be able to find electric fields of lots of charges again. We want to find the electric field of the Van Der Graaf. We want to find the electric field of a wire so we can understand how currents work. We want to find the electric field of whatever. So we're going to find the electric field of various shapes and geometries and build a common language and some building blocks for building more complicated shapes of things later. What do I mean by that? Here's the electric field of a ring. So let's see here. I'm gonna draw, I'm gonna cheat and use my ruler, which you guys can't see. So I've got like that's an axis right there, okay? And then I'm gonna try to, I don't know how this is gonna work. Yeah, that didn't work. Ah, there we go, okay? This, I didn't bring it. I'll be right back. We're going to find the electric field of this. Okay? This is a ring, right? And we're going to put charge on this ring. Okay? It's going to be uniform charge density to begin with. Okay? But I want to find the electric field of this ring somewhere on the axis of the ring. Right? So it's kind of like there's an axis that points down straight down through the middle of it, right? And what I've tried to draw up there is sort of the oblique. Does that make sense? We're not quite looking at it edge on, sort of looking on it from the side, right? I tried. Okay. So you kind of get the idea of what I was going for there, right? Okay. All right. So we'll call this like an x-axis. We will put the y-axis right there, and I don't know why my y-axis is offset like that. There we go, y-axis. Okay, so it's kind of my setup right there, right? And I'm trying to kind of sort of draw a three-dimensional drawing here. Okay, and we're going to find the electric field at that point right there, somewhere on the axis of that ring. This whole ring has charge Q on it. We'll call it positive charge, okay? And so that positive charge is spread all the way around this ring. So if I'm going to find the electric field at point P, I don't have a single charge, right? I have charge spread out all the way around this thing. So what do I have to do?
Electric fields.
Well, yeah, no, I know, but like I've got to break it up, right? Like at point P, is there going to be an electric field vector that's caused by, say, this point on the top of the ring?
Yes.
There's a little piece of charge, right? And there's a little piece of charge right here, a little piece of charge, a little piece of all the little pieces of charge, right? So if I got a bunch of little pieces of charge, I got to find the electric field from each one of those and then add them all together. And then make them infinitely small and add them together? It's like like a good day. All right. We are trying to find what? The electric field. How are we going to find it? By adding up a bunch of little electric field contributions. Is there a reason I taught you all of that integration last chapter, even though it's not in the book? No, I have no reasons for what I do in here. I'm just a madman teaching you physics. What does that little piece of electric field look like? We want the electric field of this whole ring. But what can we break the ring up into that we already know the electric field of? Points. Pieces of charge, right? Okay. What's the electric field of a point charge? PT? Electric field of a point charge? It's K Q over R squared R hat, or KQ over R cubed R hat. Those are the same thing, aren't they? Right? So you can use either of them. But if I take a little tiny piece of the electric field, am I taking a little tiny piece of K? It's a constant. No. Am I taking a little tiny piece of R? No. What am I taking a little tiny piece of? Q. It's a little tiny piece of charge, isn't it? So my dE is going to be K dQ over R cubed R vector. And now, what's the issue? What's dQ? Right? We're trying to break this down. We're getting it more and more granular until we can finally hit a point where we can match something to a physical parameter of our coordinate system. And now we're at dQ. There's a lot of things we got to figure out. We know what K is. We got to figure out what dQ is. We got to figure out what R is. And what the R vector is, right? Once we get R vector, we can find R, right? Let's do the vector first, okay? Pick a spot, any spot on that ring that seems easy to think about or even draw. I'm going to pick the top. On the y-axis, I'm going to pick a point right up here to be my little piece of charge. It's my little dQ just sitting right up there. It's a section of the ring. And I'm going to draw. Where does the electric field vector for that little tiny piece of my ring start? On that charge. And where does my R vector end? At the place where I'm trying to find it. So I'm going to draw a vector that goes straight from that little piece of charge sitting there at the top of the ring down to my point P. And then I'm going to read right off of this what that vector is. My R vector. What is its x component? It's the distance from along the x-axis to point P. What should we call that? X. It's on the x-axis, right? So if we call this distance x, right here, that means I have an x and a positive I hat because my vector is pointing positively to the right. What do I put down for the y component? Let's call the radius of this thing A. Have you noticed I don't like to use R for radius? Why do I not like to use R for radius? Because I use R vector, right, in what we're doing, right? It's a distance, right? So I'm going to put A in what direction? Negative J hat. So I now have my R vector. What is the length of R? Square root of x squared plus a squared. Whatever those numbers are. So I can come over here and write my dE. It's k, whatever dq is, all over x squared plus a squared to the 3 halves. times my r vector, xi hat plus a, we'll do it this way, negative aj hat. Negative aj. Okay. What's dq? Okay. I know you guys want to go to like lambda or something, right? Lambda or sigma, right? Because I taught you that, right? Let's just stick this up here right now and let's ask a few questions, okay? It's coming over here. It's the integral k dq over x squared plus a squared, so 3 halves, xi minus aj. This looks like a terrible integral. Mr. Vela, my life is over. What are the, let's not do the limits yet. What is constant? K is constant. So can the k come out of in the front of this thing? Okay. Is there anything else that stays the same? What did you say?
Everything but DQ.
Everything but dq? No matter where I am on this ring, does that blue vector, starting up here at the top and pointing down to whatever the point is, it stays exactly the same length all the way around? That's just that thing here in the denominator is just a distance, is it? So does that distance stay the same no matter where I am on this ring? Yes, right? Because of the axial symmetry that exists here. So the whole denominator is a constant. Okay? What about the distance x? Does that change as I go around? No. What about a? Does that change as I go around?
Up or down.
Okay. So we know that this electric field vector is going to be something like that, right? Positive charge points away. What about the one down here? Well, it's going to point up like that, isn't it? What's going to happen to every component that's not an x component? It's going to cancel. And so by symmetry, the y component is 0. The electric field has to be directed along the axis. Everything else is going to cancel itself out. Anything that tries to go perpendicular, this is the on-axis answer. If I was somewhere else, then we'd be in big trouble. Okay? But I can just say, you don't have to do the integral to prove it. It wipes itself out. Nice! Okay, and I already established that xi hat doesn't change. So that leaves me only with the integral of dq. And if I break a ring that has a total charge q on it, and I evenly cut those little q's into dq's, and then I add them all up again, what am I going to get? Q! And that's it! I'm done! That right there is the electric field for a ring of charge if you want to find the electric field on the axis. What if you're at 0? What if you're right at the center of this ring? What does it say? What's the electric field at the center of this ring if x equals 0? What's k times 0? Divided by something that's not 0. It's still 0. Right? Why is the electric field at the center of this ring 0?
Symmetry.
It just works. That's power. It's a lot of power. And when we come together on Monday, we're going to use that power to find the electric fields of disks, find the electric fields of spheres, inside and out. We're going to find the electric fields of rods and lines and all kinds of stuff. And we're going to do it by integration. See you then. I hope to see you on Friday.